So fractional crystallization. So when magma cools, it crystallizes in the reverse order that it melts. So in other words, the last minerals to melt, the ones with the highest melting points, those are the first ones to crystallize. So fractional crystallization is a process similar to, but the reverse of partial melting. So again, the same order they melt in, if you go backwards, that's the order they're going to crystallize in. Both processes change the composition of the magma because as fractional crystallization occurs, you have more and more minerals and elements taken out of the magma. So as minerals crystallize, they're removed from the magma, and eventually silica is the main component left in that magma. Okay, so again, this is our cooling rate here. So our last minerals to melt at 1200 degrees Celsius, those are going to be some of the first ones to crystallize. So they'll crystallize and form a layer down here. Then you'll have, as it cools down a little more, you're going to have different minerals crystallizing, and they will form a layer. And then you'll have different minerals, again, crystallizing until you eventually get down to just having silica left in the magma. So as an example here, as magma in an intrusion begins to cool, crystals form and settle to the bottom. Okay, so that's kind of what's happening here. You actually have this layer of sandstone here, and what they call the chill zone. We have these small crystals. Basically, the sandstone is there. This magma gets sort of injected into this area where what comes into contact with the sandstone, it may cause some metamorphism and stuff like that, but that cools those crystals down. You get very small crystals there. Then you have this area here between the two chill zones where you have the main molten body of magma. And then as it cools, crystals form and they start to settle at the bottom. So you get this olivine layer down here maybe. And then above that you get this plagioclase and pyroxene, but then no olivine produced here. And then mostly plagioclase, no olivine up here. So this layering of crystals is fractional crystallization. So each layer is primarily a different mineral. So lower layers have higher melting points and higher iron and magnesium content. And then the higher layers have lower melting points and more silica content in them. Okay, so you get this layered effect in the magma body or in the magma formation. So the end of fractional crystallization. So as more crystals are separated from the magma becomes concentrated in silica, aluminum, and potassium. Okay, so you got silica, aluminum, and potassium that's kind of left over at the end of all this. So the last two minerals to crystallize then are potassium feldspar, which is potassium, aluminum, and silicon, and quartz, which is just SiO2, which is silica. So then potassium feldspar is one of the most common feldspars in Earth's crust. It's just very common. There's a lot of aluminum, there's a lot of silicon, there's a lot of oxygen in the Earth's crust, so that makes a lot of potassium feldspar. Quartz often occurs in veins because the last liquid portion of the magma, which is almost pure silica, and maybe some other elements like gold and silver and some elements that don't get worked into a lot of minerals. But this pure silica is basically squeezed into cracks and fractures in the rock, and you end up with these veins of quartz like we have over here. So these are quartz veins. A lot of times you will find deposits of gold and silver and things like that in these quartz veins. Because those are native elements that don't really get incorporated into other minerals.